This is Mr. Parvaiz with Henrico High School. This is Work Lesson 1. In this lesson, I'm just going to go over some simple ideas regarding work and how to calculate work. So, in your textbook, you're given an equation to calculate work. To calculate work, your textbook says take force multiplied by cosine theta and multiplied by S. S over here just means displacement. You may be more comfortable using D for displacement. You can use whatever letter you want. You can use X for horizontal displacement, Y for vertical displacement, or you can just use D. Now, the reason why they're giving you a cosine theta in there because it's imperative to realize that to calculate work, the force has to be in the same direction of the displacement. For you to get positive work, the force has to be parallel to the displacement. You will get negative work if the force is anti-parallel to the displacement. Anti-parallel just means in the opposite direction. So I'm going to show you a simpler way. The way I teach the idea of work is I simply say in my equation, find the force that's parallel to the displacement and use that force. So my equation looks a little different than this, and I'll show you both equations and how they're used. So I simply say to calculate work, you need to take the force that's parallel to the displacement. And that symbol right there, the two parallel lines between the F and the D for displacement, just stands for parallel. It's a reminder that if you want to calculate the work, find the force that's parallel to the displacement. So I'm going to give you a couple of examples. In the first few examples, it's quite easy to determine what force we're going to have to take into account. As we go through lessons 2, lesson 3, and lesson 4, we're going to have to think a little bit deeper to figure out what force should we take into account when we're calculating the work that's being done. So we're going to start off by saying you have a flat surface and you have an object sitting on that surface. So in the first scenario, let's make things simple. We're going to say it's on a frictionless surface, so you don't have to worry about the force of friction. And we're going to say there's a force pulling this object to the right. So there's a force of 5 newtons that pulls this object to the right and displaces the object 10 meters. So the first question is pretty simple, and somebody asks you, how much work is being done on this object? Well, you're going to say, well, the work is being done by the force that's depicted in the picture. That force is parallel to the displacement. That force is towards the right. The box is moving to the right. That means that force is responsible for doing the work that caused the box to move. So if you were to calculate the work that's being done, you'd simply say, so in this particular case, I am using the first equation that's given to you in the textbook, which says take the force, then take the angle that exists between the force and the displacement. So if the force is to the right, and the box is moving to the right, then that means the two vectors are parallel to each other. That means the angle that exists between the two vectors is 0 degrees. So that's why I put down cosine 0. Now you are well aware that cosine 0 is 1. So basically it drops out of the equation, and it's simply 5 newtons times 10 meters. And the unit for work is going to be joules. Whenever you keep your force in newtons and your displacement in meters, your work will come out to be in joules. So you can do it this way, or you can simply use the equation that I've given you on the second line over here. I'm just going to erase my work and show it to you once again. It's going to be very similar. So I've pretty much done the same thing, except this time I just used the second equation, which is same as the first one, except it's a little simpler in my eyes. I simply asked myself, what force is parallel to the displacement? meaning which force is responsible for moving this object to the right? And the answer to that is the 5 Newton force is parallel to the displacement. The 5 Newton force is the force that's responsible for moving the object to the right. So I simply use that force. And my displacement is 10 meters, so that comes out to be 50 joules. So you can get the answer both ways. So pick the simpler method for yourself. Whatever works for you, use that. I'm just showing you both because the top equation is the one that's given in the book, but I wanted to explain to you the reason that cosine theta exists. Basically, they're saying find the parallel component. It's going to be a little bit clear in the next. Excuse me. It's going to be a little bit clear in the next example that I'm going to give you, in which the object is being pulled to the right, but the force is not going to be parallel. I'll show it to you. It'll be at an angle theta. So once again, we're going to keep things simple, and we're going to say you have a flat surface, and we're going to keep friction out of the picture right now. We're just going to keep it a frictionless surface, and you have an object sitting on the surface. So you have this object that's being pulled to the right, but the force is pulling at an angle theta, whatever that angle may be, 10 degrees, 20 degrees, 30 degrees. I'll just go ahead and put 30 degrees in for now. And somebody says, go ahead and calculate how much work was done to move this object to the right. So the first thing you've got to do is you've got to realize that you cannot use the 5 Newton force, because the 5 Newton force is doing two things. It's pulling the box to the right, and it's pulling the box simultaneously upwards. This is something that shouldn't be new to you. Whenever you see vectors at an angle theta, you know those vectors have an x component and a y component. They have a horizontal component and a vertical component. So you've got to be wise about this, and you've got to say, well, which one of these components is moving my box? Which one of these components is responsible for moving the box from left to right? So first of all, the Fy, let's talk about that for a second. You know how to calculate the Fy. You're simply going to use sine theta to calculate the Fy. That's the trig function you're going to use. But before you even calculate the Fy, ask yourself, is the Fy, is the vertical component responsible for moving the box to the right? And the answer to that is no, because an upward force has nothing to do with moving a box to the right. An upward force can move a box up, but it can't move a box to the right. So the Fy is not responsible for moving the box to the right. So you don't even have to calculate that value. You've got to calculate the Fx. You've got to calculate the horizontal component, because that's the component that's responsible for moving the box to the right. So make life simple for yourself. Just go ahead and calculate the Fx. I'm going to show you how to calculate both of them right now, but you're only going to use the Fx. As you can see, I'm using that cosine theta. That's one of the reasons why the cosine theta was showing up in the equation to calculate work on the previous slide. So cosine 30 degrees is 0.866. We multiply that by 5 newtons, and it comes out to be 4.33 newtons. That's the Fx. That's the horizontal component of force. This is what you're going to use to calculate the work down in the box as the box moves to the right. I'm going to still show you how to calculate the y component just for practice, but you're not going to need to use the y component to calculate the work. So the y component, the vertical component of the force, comes out to be 2.5 newtons. So literally this box is being pulled to the right with a force of 4.33 newtons. And simultaneously the box is being pulled up with a force of 2.5 newtons. The net force, the resultant force, being shown as 5 newtons at an angle of 30 degrees. So the question still has to be answered. What's the work done on the object as it moves 10 meters to the right? So you're simply going to use your work equation. And you're going to go ahead and plug in your Fx, your horizontal force for the force, because that's the force that's parallel to the displacement d. So you're going to use 4.33 newtons. Now remember, you calculated the Fx by using cosine theta, 30 degrees, cosine 30 degrees. That's why in your equation you see that cosine 30 degrees show up. Now you can do it like I've done it, where you calculate the Fx first and plug it in here. Or you could have simply put in 5 newtons times cosine 30 degrees, because that's what you were doing up here, 5 newtons times cosine 30 degrees to get the Fx. You could put that directly in here and then multiply it with 10 meters. Whichever equation you want to use, it's still the same thing. So both of these equations are the same thing. I just prefer finding the parallel component by itself and then plugging it in to the work equation. So that's why I calculated the Fx first. So right there, 4.33 newtons times 10 meters is 43.3 joules. So that's the work that's being done on the box as it moves to the right. Now remember, this was a frictionless surface. Keep one thing in mind. When you have positive work that's being done, just like in this example, when positive work is being done, an object will accelerate. It will have a positive acceleration, because keep in mind, positive work being done on a system, and here the system is the box, means that you are giving energy to the box. So if you give energy to the box will accelerate as it moves. If a total of negative work is being done on the box, that means energy is being taken away from the system. So if negative work is being done on the box will have a negative acceleration, meaning it will slow down. Some people call that deceleration. Now, the other scenario, the third scenario is, what if the positive work that you're doing on the system is negated by negative work, meaning the amount of positive work you do and the amount of negative work that's being done on the system both equal each other, but one's positive and one's negative. Well, if that happens, the net work is 0. If your positive work and negative work are equal to each other, then the net work is 0. And when the net work is 0, then the object will neither accelerate, it will not have a positive acceleration, nor will it have a negative acceleration. It will just maintain a constant velocity. So keep that in mind. And one good example of that is when a car is traveling, the car engine, through combustion, takes the chemical energy in the gasoline and converts it to mechanical energy. It first converts it to heat energy, thermal energy, and then that thermal energy changes to mechanical energy, because there's an explosion that's taking place when the gasoline and the oxygen combine with each other inside each of the cylinders of your car engine. So in an internal combustion engine, the gasoline is the chemical energy that changes to thermal energy, and then the thermal energy changes to mechanical energy while the engine parts are moving. So finally the wheel turns, and the tire pushes the ground backwards. Well, the ground's not going to move, so the ground then ends up pushing the tire forward through the force of friction. So that all depends on friction. If friction is strong enough, the tire will not spin out. And if friction is strong enough, the tire will get pushed forward. And if the tire is connected to the car, the whole car gets pushed forward. So basically, your car moves because of friction. Friction is actually pushing you forward in this particular case. So friction would be doing positive work on the system being your car, and would cause your car to accelerate. However, if the negative work being done on your car due to air resistance negates the positive work that's being done by the force of friction, meaning the positive work being done by friction is the same amount as the negative work being done by air resistance, then your car will neither accelerate nor will it have a negative acceleration. So it will neither accelerate nor decelerate. It will just move at a constant speed. So basically, keep this in mind. If you have a net positive work, you will accelerate. If you have net negative work, you will have a negative acceleration. You will slow down. You'll decelerate. But if your net work is 0, then you will neither accelerate nor decelerate. You will neither have a positive acceleration nor a negative acceleration. You will have a constant velocity, which means either you're at rest, if you were at rest to begin with, or if you're moving, you're going to continue moving at a constant speed. So hopefully this was useful, and we're going to continue the discussion in the next lesson.